Chapter 3.2, Rolle's Theorem and Mean Value Theorem, Day 1. Two more existence theorems, bringing the total to 4. All right? Rolle's Theorem. In order to use Rolle's Theorem, 3 things must be true. It must be continuous on the open interval, differentiable on the closed, and there must be the endpoints equal to each other in height. So for example, here is A and here is B. F of A must equal F of B. So we'll say right there and right there. They must be equal. And it must be continuous and differentiable. That means it's a smooth curve with no cusps or gaps. All right? So we do that. Rolle's theorem says that there exists at least one C on the open interval, such that the derivative is equal to 0. And we can see by the way we drew it, that there is at least one place where the derivative is equal to 0, where there is a horizontal tangent. In fact, in my drawing, I had 2. So that's Rolle's theorem. It says that it's basically saying that somewhere between these two equal endpoints, there is a maximum or a minimum. And it's not at the endpoints, it's between them. The mean value theorem, there's two conditions for use. It must be continuous and it must be differentiable. And this one's a big one. All right? The conclusion here is that there is a C in F of A. There is a C in the open interval, AB, such that F prime of C equals F of B minus F of A over B minus A. Now, in other words, the average rate of change is equal to the instantaneous rate of change. All right? So if we have an interval, pick any 2 points, it must be continuous and differential between there. All right? So we got our function. Oops. Let's draw it as a function. Right there. There's our function. It is continuous. It is differentiable on the open and closed intervals. Well, the mean value theorem says we can draw our tangent line. And that we can have at least one spot where that tangent line is the instantaneous line. In case here I got 2 spots. We can examine it there. There, the instantaneous rate of change, and I better illustrate it right there. The instantaneous rate of change is the same as the average rate of change. And this other point right down here, our instantaneous rate of change here is the same as the average rate of change on that interval. All right? This has implications for traffic. If you're going 55 at 2 checkpoints the cops set up, but between them your speed is higher than that, they know you weren't going 55 during that entire interval. Okay. Rolle's theorem, not on the AP test, but it leads very nicely to the mean value theorem. So that's why we kind of discussed it a little bit, just so we can kind of look at it. Determine, A, whether Rolle's theorem can be applied. If it can be applied, find the values such that apply to Rolle's theorem, such that F prime of C equals 0. To apply, there's 3 conditions that must be met. It must be continuous, it must be differentiable, and the 2 endpoints must equal each other on their y values, or their f values. This is a polynomial, so we know it's continuous on all real numbers and differential on real numbers, so it's definitely on the interval from 1 to 2. The next thing we need to check is what is f of 1 and what is f of 2. All right, quickly grab a calculator to do that. My function is x squared minus 3x plus 2. Squared minus 3x plus 2. All right. F of 1 is important. F of 2 is important. All right, so we can see that f of 2 does equal f of 1. All right, so we can apply Rolle's theorem, which says somewhere between 1 and 2 the derivative is 0. And so what we'll do is we'll find our derivative, f prime of x. That's 2x minus 3. Set that equal to 0, and x equals 3/2, which is really 1.5. So that is the value of c that satisfies Rolle's theorem. That is where the derivative between 1 and 2 equals 0. Okay, again, Rolle's theorem. Check, can it be applied? First, is this function continuous? Well, here, right here, when x is 0, we're dividing by 0. So it is discontinuous at 0. That is in the interval. So Rolle's theorem does not apply. All right? It doesn't matter if it is equal on the left or the right. And in fact, it is equal on the left and right. F of -1 does equal f of 1. Because it's not continuous, we cannot apply Rolle's theorem. So we just stop. The f prime of c may exist, it may not. Here, determine whether Rolle's theorem can be applied. This one is continuous. However, absolute value function has a cusp. And this cusp, in this case, is at x equals 3. So it is not differentiable at the cusp of x equals 3. Well, that is in our interval. At x equals 3, f of x is not differentiable. So Rolle's theorem does not apply. Rolle's theorem does not apply, so we do not continue. F prime of c may equal 0 somewhere in there, but we cannot be sure. All right? Finally, let's move on to the mean value theorem. When I say finally, I mean topic-wise, not question-wise. Can we apply mean value theorem in this case? Is this function continuous and differentiable? And it is, because it's a polynomial. All right, so I'm going to just kind of rewrite this as x cubed minus x squared minus 2x, and find all values of c where the average rate of change equals the instantaneous rate of change. So first, let's find my average rate of change. All right, I'll speed this up hopefully, use the graphing calculator. So my function is x cubed minus x squared minus 2x, and my values are 1 and -1. So we got -2 minus 0 over 2, so it's -1. So I need to find where is the derivative equal to -1. Well, to do that, I should probably find the derivative. That would be 3x squared minus 2x minus 2. And we'll set that to -1. -1 equals 3x squared minus 2x minus 2. To solve the quadratic, you want it equal to 0. 3x squared minus 2x minus 1. Use the quadratic formula, or you can factor. We got 3x and 1. It's got to be plus 1. Let's switch this around. So we got x minus 1. So here, 1, negative 3x gives us negative 2. So our values are negative 1/3 and 1. Those are the two values where the average rate of change equals the instantaneous rate of change. The 1 guaranteed is negative 1/3. 1 is an endpoint, so it wasn't guaranteed, it's a bonus. Right? So the value of C that satisfies the mean value theorem is negative 1/3. It's guaranteed to be between the endpoints. All right. As I was saying, it's used a lot for traffic patrol. 2 stationary patrol cars equipped with radar are 5 miles apart on a highway, as shown in figure 3.14. I didn't include the figure. You can picture 2 cars sitting there. As a truck passes the first car, its speed is clocked at 55. 4 minutes later, its speed is clocked 5 miles per hour at the second car, which is 5 miles away. Prove the truck must have exceeded the speed limit at some time during the 4 minutes. Well, mean value theorem says it must be a continuous and differentiable function. If you know anything about driving a car, you can't pop in and out of existence when driving a car, so it's continuous. You can stop, but the time is still moving on, and your speed is 0, which is still graphable. All right, so it is continuous, it's differentiable, so by the mean value theorem, somewhere you must have been driving the average rate of change. We can find the average rate of change using the distance equals rate times time equation. We know the distance is 5 miles. We're looking for the rate, and the time is 4 minutes. And in an hour, that's 4/60ths of an hour. So it's 5 miles equals rate times 4/60. Multiply both sides by the reciprocal. The rate equals 5 times 60/4. 60 over 4 is 15. 15 times 5. That guy was going, at least one point, he was going 75 miles per hour. So sometime during that exercise, he was going 75 miles per hour. And that is the mean value theorem. Somewhere in an interval, you're going instantly, you're going your average rate of change.